Welcome to this session, how to efficiently autoscale your Kubernetes cluster. So if you're connected to this session or you're interested to listen to this session, it probably mean that you are, first of all, interested in Kubernetes, because in the title, you have Kubernetes in the title. And second aspect is obviously about autoscaling. But we want to also touch base on performance engineering, things that we're going to deal with, but not in details. There will be performance benchmark results shared in this talk. So check it out. I hope you will enjoy these sessions, and I hope you will learn something out of this session. So without any more, let's start. So first, let me introduce myself. My name is Henrik Rexed. I'm a cloud native advocate working at Dynatrace a bit more than 4 years now. And I pretty much focus on areas like open source, Kubernetes, cloud native related topics, SREs, open telemetry, of course, all those aspects. Prior to my investment in the observability world, I spent my entire career as a performance engineer, testing, breaking, tuning, optimizing things, having fun at the end. I think performance engineering is the most efficient practice to discover and learn architectural concepts. So if you really want to scale up your technical skills, I think performance engineering is the best environment to do so. Because performance is in my heart, I try, if I have time, to produce content in a YouTube channel called PerfBytes, and my colleague Senior Performo is helping me to do that, and he also have his Spanish version of the channel called PerfByte Español, covering the same content for Spanish language, and I started to do the PerfByte Français. So if you want to learn French and performance engineering, check it out. It's out there. Since 3 years now, or a bit more, I have launched the YouTube channel Is It Observable? So where I provide content about observability in general. So let's start. And this talk is about a story. It's a customer story. So I'm not going to refer and make any reference to the brand or the name of that customer, because at the end we don't care about who it is. I think it makes more sense the journey they went through. Of course, I don't sharing any numbers from their environment, so I have rebuilt an environment to walk through that story. So don't pay attention on the numbers. This is a 100% demo environment, but the idea is that from the story is still there. So the main actor from this story is Kubernetes, obviously, from the name of the title of this talk, and we want to talk about cost. So at that time they were talking about cost. Maybe today we may revisit this story by taking the angle of energy, but cost is the central element of that story. So we're going to talk about the cost of our Kubernetes cluster, where we are spending on the cost, how we can optimize them, and we're going to touch base on the impact of non-optimized workload in our environments and in our Kubernetes cluster. And we will see that we will try to optimize things, and we will touch base on autoscaling. So using HPA, we'll explain what it is, of course, and show how we could be more efficient in the autoscaling journey. So once upon a time, so here I'm talking about a well-known company that has a well-known established brand and customer base, and they wanted to launch another website, another brand to target other personas and other people. So they started this fresh new brand, new design, new experience, new application. So they went through all the steps that you can imagine from this type of project. And so, of course, testing, building, deploying, doing a lot of great things, trying to build this more on a cloud and efficient way than the traditional website. And once the D-Day happened and released the app in production, yeah, everything was successful. No major problems. The performance was there. Of course, the traffic obviously is lower than the traditional brand so because it's a fresh new application, new website, so of course you expect less traffic. But at the end, everyone was successful, very proud, and then everyone was saying, now let's focus on innovation, on new features, so we can bring more value to our users. But one day someone knocks on your door, and go say, hey guys, efficient, well done, good job. But I look at the cloud billings, and the environment that we are using at the moment is significantly expensive related to the revenue that we're doing with the website. So we have to somehow optimize and reduce the cloud billings. So it's not the urgent project, but it's like a side action that they had to do when they were releasing new features. So they started this venture of let's optimize the cost. So let's cover the cost of our cluster. So everything has a price, and especially when you deal with cloud providers, when you have Kubernetes class clusters, you have different layers involved. So you have the cloud provider itself that provides your managed Kubernetes clusters, and that would mean that they manage a node, so they will take some fees about this. And then if you have any the need of pushing data out of the cluster to different region, different zones, or to internet, this is going to be charged, obviously. And then, of course, the size of the worker node that you need to run your application. So, of course, no surprises, depends on the size of the CPU, memory, GPU. And then if you need any storage, so PVC, storage always come with a price. Depending on the size of the storage required and the number of storage, you will pay more extra. And last is the network. So if you need to expose your application out of the cluster through IP address, to have an public IP address, this will come, of course, with a price. So if they want to optimize their environments, they have basically 3 dimensions. At that time, you can resize the nodes, rethink about the node pools, but there were no intentions of doing this because they were planning to deploy more applications on those nodes. And maybe we can do that right now with a solution like Carpenter and try to optimize the node pools a bit more. But at that time, it didn't exist. And then the other angle is to cover the storage with the personal volumes, but the storage with the data were intended to grow, so no intentions to reduce, so that doesn't make sense. So the last angle is basically resize the workload, so rethinking the size of our workload to optimize a bit the space that it's taking in our cluster. So that will be the angle. So how do you resize your workload? Well, when you deploy in Kubernetes, you deploy on your worker node. So if you have 3 worker nodes, each of worker node will have a quantity of CPU and memory, and this gives you the maximum of the allocatable resources. So every time you deploy, Kubernetes will look at the deployment files and what you have defined in the resources definitions, in the requests, and basically it will allocate and block from the resource available the resources based on your definitions. So that's why the request is usually very different from what we actually use. And as a human being, naturally, we intend to be a bit secure, so we try to put very high values, so not very efficient. And at the end, we are blocking a lot of resources. So here in this example, we consumed about 98% of the allocable resources with 4 deployments, and then which means we don't have any applications and any memory and CPU left in this cluster to be deployed because we have blocked everything. But now if you pay attention to the usage, you realize that you only consume about 10%, which means we block a lot of resources, but we don't use them. So it's not super efficient. So the game will be very simple. We need to reduce. So we're going to do calculate the efficiency. So compare the usage versus the request. So usage divided by the request multiplied by 100. And then the request is one thing, but you can still consume more than what you requested. That's why there is a limit. We'll talk about this later. So you can also do the exercise with the limits as well. So the journey is simple. It's an optimization process. So you start, you create a baseline to understand where you are, what are the numbers. And again, you don't do that in production. So you still need to do the baseline even if you know your application in the target environment. So you will get the numbers, know how it behaves, and then you launch the optimization pattern. So you check the current settings, you modify 1 configuration, not 2, and then you run the simulation, you analyze, so you figure out, did you improve or was it worse? If it's okay, then we can move on to the next settings, and so on and so forth. So it's going to be an iterative process. It could take time, it could be expensive, but it's worth it. There are solutions that do it automatically, but again, it comes with a price. So what tools we need? So obviously we need a couple of different tools for this. So we will need first load testing product, no surprise. So in my case, I use a lightweight load testing solution called K6 that fits pretty well in Kubernetes. And I don't need any UI from the load testing product because they won't provide me the data that I need. In this particular use case, I need more advanced insights on my environment, so that's why I'm going to use an observability platform. In my case, I use Dynatrace, so I need a tool that push the data to elsewhere, and K6 is just perfect with that because they have tons of plugins for this. Then I need to report the costs, so I'm going to use a CNCF project called Open Costs, which is will do an estimation of the costs, and an estimation is good enough for me. I don't need the real-time billing, and I just need an estimation, a live estimation, and split it by various dimensions, namespace, container, and so on. I need to get the actual throughput coming in each of those microservices. So Istio Envoy will be perfect, expose that, and it provides all the security in place with the service mesh capabilities. And to ingest that data back to Dynatrace, I'm going to use an OpenTMP collector. Once the data is back in Dynatrace, I'm able to build a dashboard where I'm measuring the CPU efficiency, so how much I'm consuming versus I'm requesting. Same thing for the memory. I'm looking at the throttling. We'll talk about the throttling later on. Namespace efficiency to see which namespaces are not efficient, and then of course the cost itself. So let's check the actual results. So by looking at the benchmark, the baseline. Sorry. So if you all this, if you want to, by the way, if you want to replicate this initiative, you can have a look. There's a repo with all the assets. So from all the solution used, the load tests, and so on. So check it out. It's on my GitHub account. So let's check the current baseline. So the current baseline with the reference architecture, after 22 minutes of the tests, we start to have an unacceptable response times. In 22 minutes of the test is about 120, less than 120 users. The efficiency of the namespace is about 25%. The cost is mainly on the CPU side. We are at about $9 and less than $1 in terms of memory. And then you can see that from the moment we have this issue, the CPU is becoming a bit unstable. So we will touch base on why there are specific reasons for that. Then let's have a look at the optimization. So we touch base on the requests and limits. And if you look at the results, you say, hey, it doesn't look very stable and doesn't look very great. That's true, but we don't care. Our intention is to take something that will take less traffic and have more replica. So here we can say that after 10 minutes of the test, we start to be quite unstable, and 10 minutes of the test corresponds to about 80 users in total. The efficiency is slightly better, but still 26.8%. And then if you look at the costs, we are at $2.4. So we already went through 9 to 2.4. But again, it's not our target solution because we still have unstable response times. And the CPU again, it starts to behave acting weirdly from the moment we have unstable situations. So first, why do we have this unstable situation? Well, that reminds you how it works in Kubernetes. So touching base on request and limits. So let's first start with the requests. So when you deploy resources in Kubernetes, Kubernetes is playing like a Tetris game. So you have different nodes available. So he has a shape coming in, so deployment, and then he looks at the size of the deployment. Is it a big one in terms of resources, smaller one, whatever? And then he's going to try to put it on an available spot in one of the nodes based on the resource definition. So basically the request is basically very crucial because it helps Kubernetes to schedule properly the workload. So the CPU will be defined in media core, the request in memory will be defined in bytes. So if you do the right tests, then no surprise, it's going to be quite easy to define. So nothing very difficult. People intend to put very high values, and that's a big, not good practice, because at the end we will block resources on the nodes, so we will not utilize our cluster efficiently. I mean, the nodes of our cluster efficiently, because we will allocate resources for nothing. So again, try to put the right requests and then just putting high values, because at the end those resources will be allocated. Then the second piece is the limits, because request is just allocating, and then nothing blocks us to consume more than what we've requested. So less or more, of course, but we can go further than the actual request values, and this is that's why we need to define limits to block the actual consumptions. So this limit is a bit of contract that we set with the owner, so Kubernetes. How much power can I consume? How much water can I consume per month, and so on. So here it's the same concept. So we will define how much memory can I consume, and if I reach the limits, then I'm going to be dead. So Kubernetes will kill my workload. So it will send an event called omkill, so out of memory. And then if I'm killed, then our pod restarts, and which means if we are killed, then our application is unstable. So we'll have a lot of failure rates behind the scene. The second piece is the CPU. So CPU here is defined not in millicore as we expect, but in function timing. Why? Because it's an heritage of it's Linux virtualizations. So it's used as C group and CFS. And the way it works is we are sharing CPU cycles. So one CPU cycle is 100 milliseconds. And so we're going to define how much time can I consume in that CPU cycle. If I define 20, I will work 20 milliseconds. And then the 80 minutes left will be basically waiting for the next CPU cycle. Once the next CPU cycle starts, I can restart working 20 milliseconds, and then again, I will be blocked. So this concept of working, posing is called CPU throttling. So we were waiting for CPU. And as you can imagine, a process trying to work and he's not able to work because he just has no CPU, it has a significant impact, specifically on the response times. So what we've seen with the response times and CPU being not consumed, it's behind the scene, it's CPU throttling. So we decided to pick to handle less traffic, but have more replica, so scaling. So in Kubernetes, you can scale easily because there are core components that help you to do that. So HPA, Horizontal Pod Autoscaler. So if you don't use HPA, you have a deployment or stateful set, and you will have to define a static number of replica, which is not efficient. So the HPA basically you will define the minimum replica, the maximum replica, and when to scale. So based on a value, you will rely on the default metrics exposed by the Kubernetes API, so which is CPU usage and memory, and basically covers most of the objects, so stateful set, deployment set, and so on, replica set, deployments, everything is supported by HPI. So that's great. And so what should we scale in our application? So we're going to cover most of the components that are very critical to our business. So the front end, responding to our users, and all the components that make business, so the checkout, the product, the cart, the recommendations, all everything that is basically a dependency for the front end. When you do any auto scaling, what is very important is not pick the value when you actually need the replica, because at the end you have to consider that a pod will take time to be scheduled, to start, to load your code, and to be actually available to certain traffic. So usually it can take 1 minute, maybe sometimes more. So you never take the actual value. So you always have to pick a value before. So it's like here let's take an example. Here are the load tests. I decide that here I need the replica. So I will go back in time and I will say, okay, 1 minute before, that is actually, this is the value that I need to set in the HPA. So then it will trigger the autoscaling exactly when I need it, and I will have the replica in time. So that's a really important concept that people sometimes forget, but this is very important. So let's check the results with using HPA on CPU usage, because there are two metrics available, CPU and memory. And if you look at the numbers, so especially the response times, you can see that at 20 milliseconds, we have the front end, which is our most important component, and also the product catalog, which is, we want to have people looking at the product, is completely unstable. Which is quite disappointing. So 20 minutes of the tests, we have about 100 users, 110, 120. So it's slightly better than we had before, but again, it's not the results that we were expected. So the CPU is kind of growing over time. So And then the number of replica is kind of growing also over time, so that's what we expect. In terms of efficiency, we're at 71%. That's a good good number. In terms of costs, we are slightly better, but no revolution. So it's not the best thing. So and then the question is, why do we have this behavior with the response times? And I checked in Dynatrace, and the increase of response times was due again to CP13. So again, CPU usage is not the best for our use case. So I thought, yeah, let maybe check the number of throughput of each individual microservices. So we have Envoy, and Envoy provides that information. So I can use either the TCP connect or TCP or connect KPI, or maybe the hit per seconds. But I thought, let's use the TCP connect, because it will be a very significant number. If I use the number of connection coming in, and I rely on this, I should have better numbers. So the problem is that I don't have this. It's a custom metrics. It's not exposed by HPA by default. So how can we do that? Well, there's two solutions. The first one is metric adapter. So metric adapter is a way of creating like a component that will do like a dictionary, so a translation from the Kubernetes metric to a backend like Prometheus, for example. So it kind of works. But the problem with this is that it's only supports, there are only few available adapters available in the market. So Prometheus, Datadog, and that's it. And then the bigger disadvantage is that you can only have one adapter per cluster. So I cannot have let's say Prometheus in Dynatrace. That is not possible. So that's not our solution. So what are the other solutions available? So yeah, there are several solutions, or Keptn, if you heard about this. And then there's Keptn. So here I'm going to touch base on Keptn. Keptn it provides a unified metric server that extends the Kubernetes metric API server. And you have the options to basically create providers. So it could be Datadog, it could be Dynatrace, it could be Prometheus. There is plenty of them available. Once you have a provider, you can define a metric, and then metric basically will be available in the Kubernetes metric API. And then you can use that metrics, of course, in HPA, but not only. There's plenty of other use cases where you can rely on Kubernetes metrics. So then chaos engineering, Argo. So there's plenty of things where you can basically extend by having custom metrics used as a reference. So what do we need? So first we have the metric server of Kubernetes. So you will have it by default. We'll deploy the metric operator of Keptn, and then we will deploy a metric provider. So here is basically defining how do we connect to the backend holding the metrics. So in my case, Dynatrace, so I will have a URL, a token. Then I will define a metric. So what is the query on this backend, Dynatrace in my case. So the query structure will depend on the backend. So in case of Prometheus, it will be PromQL. So I'll define the query on how to extract the metric. And once the metric exists, I can make a reference in my HPA. So here I can make a reference to an object, and I'm making a reference to the Keptn metric object, and I can set the right thresholds to autoscale. All right, so let's check the results about the usage of TCP Connect in our Envoy proxies. And when I looked at the results, I was super disappointed. I mean, I was not expecting that. So you can see here, at the 5 minutes of the test, we have an increase of response times, which is okay. We don't have that before. And then we somehow have the response times start to reduce. And then after 25 minutes, it's completely unstable. So at the end, we almost have a regression, less load supported in our environments than we had initially, and with the previous version that was even provided better response times. The CPU is kind of interesting, and the number of pods you will see, we'll talk about later, is surprising. But there's a reason. If you look at the namespace efficiency, we are at 31%, so this is also disappointing. And the cost is okay, but we don't care about the cost, because at the end we have we're gonna take this solution. So why do we have this behavior? Well, it's pretty much simple. At the beginning of the tests, our architecture, and so the front end, here's the front end. So the first component, and then he basically he addressed the request behind the scene on all the various components. So at the beginning of the test, he received a lot of things, and then he delayed. He pushed the request to other components, and those components are responding fast, and then the load increase. So at the beginning, it's very fast. So we get a lot of TCP connect. So at the beginning, the HPA says, "Oh, okay. So there's a lot of TCP connect. Let's add more replica." So you can see here at the beginning we have more replica than expected, and then because it's slowing down, on the dependency are slowing down because of the load, then we start to have less TCP connect because it's slowing. And at the end, he says, okay, so there are less TCP connects, so I'm going to remove replica. So we have the exact opposite behavior that we thought of, where we start with a lot of replica, and then he says, okay, I'm going to remove replicas with the load, and at the end, it's a catastrophe. So this is where, by surprise, it was not the right KPI. So after some reflection, we said, okay, let's pick, why don't we pick the, we know that CPU throttling is impacting our workload. So why don't we take this? Why don't we take throttling as a reference? So we did the tests, and so we use CPU throttling, and you can see that we have a spike here at 30 minutes of tests. But again, we redid the test, and we didn't replicate that behavior. But at the end, with this KPI, we have better response times, better than the initial baseline, better behavior of the CPU, support more load, and then the number of replica is quite unstable over time. If you look at the CPU efficiency, we are almost at 50%, so 47%. So remember, we started at 25, so much better. And then on the cost, we are at 1.61, and on the memory at 0.2. So we almost divided by 8 the actual cost of the environment, and having better response times. So that is exactly what we were looking for, and HPA was the proper solutions to do that. So as a small takeaway, so first, optimize your resource allocations. I mean, there's more than 60% of the Kubernetes users that are not efficiently using the resource allocations properly, so their cluster is not optimized. So they are over-provisioning resources for nothing, and we should stop doing this. Define resource quota to avoid eating resources from your neighbor, and then apply HPA. So HPA, like I said, is crucial, but don't rely on the default metrics CPU and memory, because they are, most of the cases, they don't fit to our use case. Don't use the throttling as a reference. It was just an example. Maybe there are other KPI that makes more sense for you, and you will have to anyway test the value of that settings. Report the costs. Again, the cost is an example, but you can also report the energy consumptions. So cost or energy at the end. If you save energy, you save costs at the end. So one or the other, but I think energy is make more sense with today's world. But measure, moreover, the efficiency of your workload. So comparing the usage versus what you requested, to always keep that in eye to optimize a bit more the usage of your cluster. Yeah, that's it for today. So a small teaser about is it observable? Check out, it's out there on YouTube. There's content about HPA, content about Keptn, content about the autoscaling in general. There's plenty of content, so check it out. If you love it, let me know. If you hate it, let me know, because at the end, with bad feedback, usually you can understand and try to improve yourself. So please look at it and share your feedback. That would be very helpful for me to improve the content in general. So thank you so much for taking the time to listen to this talk. If you want to have more details on or touch base on me, you can find me on LinkedIn with my first name and last name, so Henrik Rexed. You can also check it on X, but usually X start to be a little bit less active on X, to be honest. But yeah, LinkedIn for sure, and of course with the easily observable HTML, you can easily reach out to me. All right, so thanks a lot for your time, and if you have any questions, I will be very delighted to answer your questions.